Alrighty, what would you guys care to look at today?
Well, first of all, I'd like to establish if there are any new formulas that need to remember.
So it is actually fantastic that you brought it up. Dr. Harbour asked me, his students were asking, I was about to say whining or complaining, but asking whether or not there would be an equation sheet available for the exam. And Dr. Harbour asked me what I thought about it, and I told him that I didn't care as long as I didn't have to make it out. So he has made one out. So that equation sheet will be available to everyone. It will be attached to your test, and I will also send you a copy of it this weekend so that you may look at it and familiarize yourself with it prior to the exam. So I believe that probably answers all equation related questions. I don't know. I don't like the idea of an equation sheet, but since he made it, I'm not going to stop you guys from using it. To me, that's just an excuse for you to not study, because you're going to be like, oh, the equations will be on the thing, and then you're going to get to the test and not know what to do and do poorly. So we shall see. Yeah. All right. So any other?
It's not nice knowing I don't have to remember a bunch of letters.
There's only 26 letters in the alphabet, in the English alphabet anyway. It is cumulative. So roughly 30% of the exam will be material that was covered on exam 1. Roughly 30%. Explicitly, that's a transient analysis problem for the exam 2 material. So you do need to refresh yourself on how to do that. My best, so for the exam 1 material that will be on the test, as far as the circuit analysis problems go, there will be, I think I'm going to dedicate 6 total questions. So that will be 2 to 3 circuits in which I expect you to be able to apply basic DC circuit analysis techniques like nodal analysis, mesh analysis, KVL, KCL, Ohm's law, that kind of good stuff. So that's the exam 1 type material. For the exam 2 material, there will be 1 circuit that will involve you doing the Thevenin and Norton equivalent. I have not yet decided whether that circuit will have a dependent source or not. My best guess is I'm going to include a dependent source, but I may decide not to for whatever reason. Don't know, haven't made it yet. That's what's on the itinerary for this weekend after I get all the videos and stuff uploaded, which I'll talk to you guys about in a moment. And then the remainder of the exam 2 material will be a transient analysis problem. And then for the exam 3 material, let's see. I would anticipate having at least 1 time domain problem that you will have to switch to the frequency domain and then perform circuit analysis on it. I would expect 1 circuit that is in the frequency domain already that you will need to analyze and perform some sort of power analysis on. And then I would anticipate there would be 1 to 2 problems regarding power factor correction. So something like has been on previous tests where I ask you about what the power factor, what PF old is, and then you use that information to find PF new in the second half of the problem kind of thing. I do not expect you guys to be to have to remember tons and tons of trig identities. That being said, I think they're already on the equation sheet if you, for whatever reason, feel you need them. I strongly don't think you will. The biggest trig identity that you would potentially have to use would be converting a sine function into a cosine function to get the correct phasor value for it. That's the extent of the trig that I expect you guys to have to memorize, which is why I'm opposed to the equation sheet. If you can calculate the complex power S and you can remember how to convert a sine to a cosine, it's all the math you're going to need for the test. So the equation sheet's probably going to have 30 more things on it than you actually need. So any other questions regarding what types of materials, et cetera, will be on the exam.
25 questions, roughly.
25 questions exactly, just like the previous two tests.
So basically, like, it'll be similar to the graphic exam, but more intense.
That is exactly right.
Will be like word problems, like, will there be like
That I haven't decided. I would think so, but I think I would lean towards like one of those short answer questions from exam one material, one from exam two, and then 3 from this new material. The types of questions I might ask you from the new material would be, let's say I give you an impedance and I ask you to tell me whether it's going to operate at a leading or lagging power factor. You could tell that based purely on the angle. If it's in polar form, or if it's in rectangular form, you could tell me if the J has a positive sign, it's lagging, and a negative sign, it's leading, that kind of stuff. So nothing really mathematically oriented. I believe in the practice exams, I traditionally also ask a problem, or in the exams that have been uploaded, I traditionally ask a problem where I give you 3 to 4 complex numbers that you can store in your calculator and ask you to do some sort of mathematical manipulation. I will probably continue to ask that style question. At this point, you should be pretty dang comfortable with doing all the complex math on your calculators. If not, we can talk about stuff. Yeah, I can't think of anything else really. So following the same basic format of the
Following that question, I know we have a few short answers where it's like, you know, what's the formula for X, Y, and Z? I'm guessing you have the equation.
probably not going to show up. That's correct. Let me check my email and see if Davis has sent me the equation sheet. I should probably not be sharing all of my emails, so let me do this real quick. I don't want you guys to judge me for having 785 missed messages on one of my accounts. Let's see. Yeah, all right, so let's open this. And let me share it in Zoom. All right. So this is the equation sheet that I believe Dr. Cronk made, I don't know, a year or two ago or something to that effect. So it has on there the equation for finding omega if you know the linear frequency, the impedance of an inductor, the impedance of a capacitor. It specifies the effective value for a voltage. He says that that's VDC, which I don't really argue with that. But that equation can also be used for currents, obviously. The RMS value is the magnitude divided by the square root of 2. That's only applicable for sinusoidal functions. Power is the product of a sinusoidal voltage and a sinusoidal current, but for some reason he doesn't have it Im cosine omega t plus phi for whatever. Average value of the power is the integral of the power over one period divided by the period. That's technically true for any periodic function, regardless of whether it's power, voltage, current, etc. Power factor is defined as the cosine of theta v minus theta I, which is true, or also P average divided by the apparent power, which he denotes as AP, as opposed to S without a bar over it. All that kind of stuff. Average power is the RMS voltage squared divided by the impedance, which is I think it would be just the real part of the impedance. I don't know. This is Davis's problem. If the equations on here are wrong, it's not my fault. I don't want anything to do with this thing, just to be very clear. Let's see. I'm not entirely sure what he means by that P. So all of these equations, that's kind of what I'm looking at here. All of these equations are related to the new material that we've covered. Exactly. None of them are for, say, the current voltage relationships for capacitors and inductors, which would have been exam 2 material, which is still going to show up on the test. So, you know, make sure to think about things like that. Davis may go back through and change it to include that. My best guess is he's just as busy as I am, so he's just going to assume that whatever Dr. Cronk did a couple of years ago is good enough because we used it then, so I guess we'll use it now. So I would not anticipate him making any changes to this, and I know for a fact I'm not going to. So just want you to be aware that because it's cumulative, this equation sheet is only valid for most of the material that we've covered after exam 2. So all of the old equations, so relating energy and power, current and charge, and then the voltage current relationships for resistors, capacitors, and inductors are all still fair game for stuff you're expected to actually know. All right, I have received 2 emails to this point. I anticipate I'll probably get another 1 or 2 regarding the videos because I kind of stopped putting them up when people stopped asking me about them because I got busy and forgot about it. So I'm going to be working on that this weekend, uploading all of the Zoom lectures to YouTube. I'm going to try to get that finished tomorrow so that you guys have a little bit more time to go over all that kind of good stuff. So yeah, what else we need to talk about today? All right, let's see. Let me go to Moodle real quick. Here. All right, so you said exam 3 from fall, right? Oops, that's the wrong thing. I don't want to move it. Cancel moving it. Exam 3 fall 2019. All right. Which question were you referring to again? I'm sorry. Number 2. A 48-volt battery is connected to a resistive network for some amount of time. If power of blah, blah, blah watts is supplied by the battery, the amount of charge that flows through the network is closest to. All right, so you're given voltage, time, and power, and you're trying to find charge, right? So I'm not going to bother solving it numerically. So voltage is a known, time is a known, power is a known. We're trying to find Q. So power divided by voltage gives us current, right? Where current is simply charge over time. So Q is energy per volts. Yeah, which makes sense because a volt is defined to be the amount of work it takes to move a specified amount of charge from one point in the circuit to another. So energy divided by voltage then should give you charge. And just to be clear here, charge per unit time is current. So, all right, next question. Exam 3, winter 2020. Problem 6, you said? All right, so enable editing. Control. All right, so the number of time constant takes a capacitor to decay to exactly 20% of its initial value is closest to blank. So we want e to the minus x over actually just e to the minus x is equal to 0.20. Because if x is the number of time constants and we divide that by tau, the duration of a single time constant, that's what's going on here. So if we take the natural log of crap, both sides, what the heck is going on? So this means negative x is the natural log of 0.20. So x is negative natural log of 0.20. And let's see, where's the natural log button on my calculator? 0.2. Oops. Negative 1.609 is positive 1.609. All right, next question. 32. Alrighty, so we want the RMS value of this voltage waveform. So V effective is going to be the square root of 1 divided by the period. What's the period in this case? Sure, so 2 seconds. The integral, oh, dang it. Okay, that's going to drive me nuts. Is there a way to just advance the pages? There we go. Okay, so we're going to integrate from 0 to 2 seconds of our voltage waveform, which we're told is 3t squared. And we always are, since we're finding the RMS value, we have to remember to square the voltage waveform. So this is then 1 over 2 seconds, the integral from 0 to 2 seconds of 9t to the 4th power dt. When I square 3t squared, I get 9t to the 4th, right? 3t squared times 3t is, yeah. Which is 1 over 2 seconds. So let's see, when we integrate that, it's going to give us 9/5 t to the 5th power, evaluated at t is equal to 2 seconds and 0, which is the square root of 1 over 2 seconds. That's looking too close to 25 for my comfort. 9/5 times T to the 5. So let's see. 2, 4, 6, 8, 16. Sorry, 9/5 times 16 is 0.5 times 9/5 times 16, square root of 14.4. That's not going to be 5. 32, thank you. I did it wrong on my fingers. Square root of 28.8, here we go, which is 5.367 volts RMS. So that's my fault for not putting volts RMS as the unit on all that, but next question. Spring 2019. Sure. Oh, op amps will definitely be on there, 100%. They're at most two problems. So one op amp circuit, and as you've probably seen on all the old exams, I ask two questions. What's the voltage present at the non-inverting or inverting terminal? The answer to those questions is the same thing because of op amp rule number 2. And what's the voltage present at the output? So that's at the output. So I'll ask you what the voltage present at the input is, and then at one of the input terminals, and then what's the voltage present at the output terminals, and that's it. All right, so spring 2019. All right, number 2. Okay, so I give you energy, and I give you a time of 1 day. So energy, I'll do it right here. So energy, which is W, divided by time is power. If I divide power by voltage, I get current. Done.
Okay. Yeah, I had a feeling it was probably similar to what you showed before.
Mhm. All right, let's see. We are given energy, and we are told the voltage.
I'm guessing it's a similar thing.
Yeah, so in this one, to get the power, we would take the derivative of the energy. So at 11 seconds, our slope here is, let's see, 2.5 divided by, so 2.5 joules divided by 2 seconds is 1.25 watts. 1.25 watts divided by 10 volts is 125 milliamps. So once we get the power by taking the slope of this curve, we divide that by the voltage because power over voltage is current. And so 1.25 divided by 10 is 0.125 or 125 milliamps. Next question, unless you've got a further one about this one.
Right. 0,
Yep.
Number 31.
31. All right, what is the period?
Oh, sorry, you asking me.
I was asking anybody. Dang it. 31. All right, V effective is the square root of 1/7 seconds. So this is a piecewise function, right? So let's look at it over the interval from 0 seconds to 7 seconds. So from 0 to 2 seconds, it has a value of 7 volts. From 2 seconds to 3 seconds, it has a value of 2 volts. I'm running out of room here, so I'll sneak it down here. 3 to 6 seconds, it has a value of -5 volts. And finally, from 6 to 7, it has a value of -2 volts. So this whole thing is under the square root. So that would be square root of 1/7. So let's see, so it's going to be 49 t evaluated at 2 and 0 plus 4t 3 2 plus 25t 6 3 plus 4t 7 6. So that would be square root of 1/7 times, let's see, 49 times 2 plus 4 plus 25 times 3 plus 4. All right, so 49 times 2 plus 4 plus 75 plus 4, it's 181. So square root of 1/7 times 181 is 5.085. So when it's a piecewise function, you square all the different parts of the piecewise function and integrate over the time intervals associated with each part of the piecewise function.
When you're doing those capacitor architecture problems, you use integral when you're looking for when you use integrals.
So if you have a capacitor and you know the current and want the voltage, you use an integral. For an inductor, if you know the, hold on, this will be easier. Let's see, so yeah, if you know the, for an inductor, if you know the voltage and want the current, you use an integral. For a capacitor, if you know the current and want the voltage, you use an integral. It's an entirely different bag of cats, in my opinion, because, sorry, VC, for the RMS value, you're doing much more than taking the integral. You're taking the integral of the signal squared, and then you're taking the square root of it because you want the root mean squared value.
Whereas in this case, we just
do the like finding the area.
Right, and this like, the reason why, let's circle back to that thing. So the area under this would be trivial to find. The problem is that we don't want the area under this curve. We want the area under the square of this curve, which is significantly different. Next question. Problem 3 from in-class assignment. Something, let's see, a file, open. I can do that literally anytime somebody reminded me to do it, so send me an email. I have them all finished from months ago. Let's see, I think that's when I first. All right, in-class assignment, 23, you said? Is that correct?
Uh,
22, problem 3, okay. So this is a problem we're talking about, right? Okay, find the average power absorbed by each element in the network shown below. So which way do you want to do this? And so by that, I mean, this in-class assignment is technically from a time before we knew about effective values and complex power relationships. So do you want to do it using the, I don't know, I guess the other way of doing it, or do you want to use the complex power relationships? The other way, okay. All right, so then let's see, I'm going to define this voltage as VR, this voltage as VC, this current as IC, this current as IR. And we can see obviously that the voltage drop VR is going to be the same thing as the voltage drop over our current source. I'm just going to label it for the sake of argument. And similarly, let's see, we want power absorbed. Okay. So actually, if we want power absorbed, the current should be flowing into the positive polarity terminal. So that means VCS and VR are the same thing, but opposite polarities. And this is going to be our current through our voltage source, which is going to be exactly equal to IC. So how I would go about doing this, I think would be superposition. That's how I would look at this, and I think that would be the easiest route. So with current source on and the voltage source off, we are going to have 12 angle 0 degrees amps. Here is VR single prime. Here is VC single prime. This is a short circuit, actually. So it's because that's a short circuit, I'm going to move it. Over here, doesn't change anything, just make it a little nicer. And I'm just going to make a note over here that obviously IVS single prime, the current flowing through our voltage source would be the same thing as IC single prime. So my voltage source is turned off, which means the voltage by definition is 0, but that doesn't tell us anything about the current. So I'm just keeping track of that. All right, so Using current division, I would say that IC single prime is going to be 12 angle 0 degrees amps multiplied by, oh, I should write down these values, minus J2 and 4. So the current through the capacitor is 1 over minus J2 ohms divided by 1 over 4 ohms plus 1 over minus J2 ohms, which is going to give me 12 angle 0 times this fraction minus 2. 10.733 with an angle of 26.565 degrees amps. Using Kirchhoff's current law, I can then say that IR prime is 12 angle 0 degrees amps minus 10.733 angle 26.565 degrees amps which I get to be 5.367 with an angle of minus 63.435. And from this, VR is 4 ohms times IR, 5.367 angle minus 63.435 degrees amps. (21.466) with an angle of minus 63.435 degrees volts. And just as a sanity check, VC prime will be minus J2 ohms times our current through our capacitor, 10.733 angle 26.565 degrees amps. And the answer we get for VC prime should be the exact same thing we get for VR prime. This is just a way to make sure I haven't made some dumb mistake. I get 21.466 with an angle of negative 63.435 degrees volts. Let's see. While I'm over here, VCS prime, the voltage drop over my current source is the same as negative VR prime. So that's going to be 21.466 angle 116.565 degrees. The voltage source prime is 0 because we turned it off, so that has to be 0. I current source prime is 12 angle 0 degrees because that's just our current source being on by itself, so it's fixed. And the current flowing through the voltage source is IC prime is 10.733 angle 26.565 degrees amps. All right, so that's every and any possible quantity we could want to know in our circuit with our voltage source off, current source on. Now we do with VS on and CS off. And so that's going to be the value of that guy, 4 angle 30. All right, so that's what our circuit looks like. So just some of our known things real quick. We are going to have our current source is 0 amps. Obviously, no current can flow through the open circuit. So that's it being turned off. Our voltage source is 4 angle 30 degrees volts. All right, so let's see. I would solve for VR using voltage division. So that would be 4 angle 30 degrees volts multiplied by 4 ohms over 4 minus J2 ohms. .578 angle of 56.565. VC is going to be, so if I do a Kirchhoff's voltage law loop around this thing, I have VC is positive polarity on the left. So let's see. So VC plus 4 angle 30 minus VR is equal to 0. So VC is going to be VR minus 4 angle 30 degrees volts. .789 with an angle of 146.565. I'm just, let me double check this equation here so I don't make a mistake later. So I'm saying negative VR plus VC plus 4 angle 30 degrees is equal to 0. So VC is equal to VR minus 4 angle 30. That algebra checks out, right? Okay, just wanted to make sure. All right, our current, stop being difficult, there we go. So IR double prime will be VR divided by the resistance, 3.578 angle 56.565 degrees volts over 4 ohms. .894 angle 56.565 degrees amps. IC is the exact same thing as IR, but in the opposite direction. Everybody sees that. So let's see, 56.565 minus 180
is 0.894 angle negative 123.435 degrees amps. So IVS is the same thing, 0.894 angle negative 123.435 degrees amps. And lastly, VCS is negative VR. So that would be 146.565 minus 180, 1.789 angle negative 33.435 degrees volts. All right, so we have all of our different quantities. So VR is simply VR prime plus VR double prime because we're at the same frequency. So that would be 21.466 angle negative 63.435 plus 3.578 angle 56.565 19.919 angle negative 54.485 degrees volts. Our current through our resistor is IR plus IR double prime. So let's see, that is 5.367 with an angle of negative 63.435 plus 0.894 with an angle of 56.565 . 4.981 angle negative 54 point. I'm getting 492. That's just rounding error, but we'll call it that. The angle should be the same between the current and voltage. So from this, the average power absorbed by the resistor is 1/2 the magnitude of the voltage, 19.919 volts, the magnitude of the current, 4.981 amps, times cosine of theta V minus theta I, which should be 0 for a resistor. So I'm just going to call it 0. And so this is 0.5 times 19.919 times 4.981. We get 49.608 watts. So pretty close with a little bit of rounding error. And we would repeat that process of adding all our voltage for our capacitors together and inductors, and then just do the exact same process, but 3 more times.
We have solved it model for current.
You know what, that probably would have, now that I'm looking at it and you mention it. So the question there is, could we have solved this thing using Kirchhoff's current law? So if we considered, let me put a different color here. Put that guy as ground. Let's call this guy Vx. That's the only unknown voltage. So we could have avoided using superposition, but I didn't notice it. So yeah, you're 100% right.
Yeah, well, in the example, I was not to look at it from model for this case.
Right.
We will find problems that require us to use superposition or source transformation and all that.
Mhm. Yeah, so for this problem, we could have done a source transformation to transform this guy into a single loop circuit, which would have allowed us to calculate VC, IC, and IVS in one go. And then we could have done a source transformation on the right-hand side, which would have allowed us to calculate VR and IR and VCS without doing superposition. So there's always going to be multiple different ways to approach this. I'm slightly frustrated at myself that I didn't notice what would be the most easiest and concise way, which is exactly what you suggested. KCL at the top node gets us there way, way faster than all that superposition I just did. So, yeah. So good job for noticing that. I feel like a jackass. So.
I'm feeling like that for I'm glad you feel the same way I do.
Okay.
Do winter 2019 problem number 9.
Winter 2019, problem number 9.
And after that, I'd like to do a couple problems that differentiate finding power factor when it's absorbing or when it versus when it's applying power. And also the inherent reactor power.
Okay, so hold on. So number 9, which of the following time domain signals would be?
Winter 2019.
Oh, that's winter 2020. I'm sorry. Let's see. So an entirely different test. Oh, wait, that's not what I wanted. That's what I want. All right, which of the following loads will operate at a lagging power factor? B. The reason why it's B is because it has an inductance and a resistance. So the reason why E doesn't operate at a lagging power factor is because it's purely inductive, which means its power factor is 0, and 0 is neither leading nor lagging. So anytime your load has some resistance and some inductance, it will operate at a lagging power factor. D and F would operate at a leading power factor because they have a resistance and capacitance. Like I said, E operates at a power factor of 0, which is neither leading nor lagging. A operates at a power factor of 1, which is neither leading nor lagging. And C operates at a power factor of 0 as well, which is neither leading nor lagging.
What happens if there would be capacitors?
Still leading. So let me prove that. With things in series, it's actually really trivial to prove. With them in parallel is where it gets more difficult. So let's start here by defining a couple of things. So our power factor is leading if theta V minus theta I is negative, right? And our power factor is lagging if theta V minus theta I is positive, right? So let's consider the first case where we have a resistor in series with an inductor. The impedance of this guy is R plus J omega L, right? So if we plotted this on a a complex plane, where this is the real part and this is the imaginary part, the impedance would have an angle like this, which I'm going to call this theta Z. Now, impedance is defined to be phasor voltage divided by phasor current, which would be Vm angle theta V divided by Im angle theta I, is Vm over Im, the magnitude of the impedance, divided by theta V minus theta I. So the angle of the impedance is the exact same thing as the power factor angle, okay? So on our graph, we can see that our impedance angle is positive, which means we have a lagging power factor. So anytime we have a resistor in series with an inductor, our power factor is lagging because the angle is positive. Now, right, it's angle 0. It's the real part. So let's see what happens if we have an inductor in parallel with a resistor. So here's R and here's L. So our impedance Z is going to be R times J omega L divided by R plus J omega L. Those two elements in parallel. So we can, in the numerator is the product and in the denominator is the sum. I'm going to multiply this by R minus J omega L divided by R minus J omega L, which is just a fancy way of expressing the number 1, right? That has the same numerator and same denominator, that's simply multiplying by 1. And so what that's going to give me is, let's see, I don't know who is texting me, but they need to leave me the hell alone. It's my wife sending me a meme. All right. So R squared minus J omega L R, so that's me multiplying this R by the numerator of the right-hand side. And then I'm going to have plus, hold on, let me make sure I'm doing this right. No, I was about to FOIL it out, but that doesn't make sense because this isn't adding. So I'm going to have J omega L R squared. So that's me multiplying this guy by that R.
Why is all of that?
Yeah. So this is the expression in, so the left-hand side is the two elements in parallel. So that I have an impedance of R in parallel with an impedance of J omega L. The right-hand side, I am manipulating this to make it a rectangular form complex number because I want to show you something. So now I need to multiply R times J omega L times negative J omega L. So that's going to be, so J times negative J is what? All right, and what's J squared? You shouldn't need a calculator to do. All right, so negative 1 is positive 1. So plus R omega squared L squared. So the R is coming from here. J omega L times negative J omega L gives me the omega squared L squared. And in the denominator, I'm going to have R squared plus omega squared L squared. So I can expand this out a little bit. So I'm going to have R omega squared L squared over R squared plus omega squared L squared plus J omega L R squared over R squared plus omega squared L squared. So even though these two guys are in parallel, the positive sign on my imaginary part, or there's a positive sign attached to my imaginary part, which means my angle, by definition, will be positive, which means when I have a resistor and an inductor in parallel, I get a lagging power factor. And when I have a resistor and inductor in series, I also have a lagging power factor for the exact same reasons If I did this for a capacitor, we would see that it's going to have a leading power factor regardless of its whether or not the resistor is in parallel or in series with the capacitor. So that's why I can look at this exam and tell you specifically electrical load A has a power factor of 1 because it's a resistor. So electrical load B has a lagging power factor, C has 0 power factor, D has leading, E has 0, F has leading. The power factor is 1 because cosine of theta V minus theta I is 1, right? So that's why it has a power factor of 1. For our capacitors and inductors, we know that there's a 90-degree separation between the voltage and plus or minus 90-degree separation between the voltage and the current, depending on whether or not we're looking at the inductor or the capacitor. Cosine of 90 is 0. Cosine of negative 90 is also 0, which is why C and E have 0 power factors.
Basically, for this problem, the numbers don't matter.
No, if exactly as I just stated a moment ago, if it's a resistor connected to an inductor, it operates with a lagging power factor. If it's a resistor connected to a capacitor, it operates at a leading power factor.
And I'm saying that the 30 ohm.
Yeah, none of those matter remotely. All right. The what? Sure. Here we go. All right. So not a straight line. So J to the first power is simply J, which is by definition the square root of -1. J to the second power is then the square root of -1 quantity squared, which is -1. J to the third power is J squared times J to the first power. So that's -1 times J, or just -J. J to the fourth power is J squared squared, so -1 squared is +1. And then J to the fifth power is J to the fourth, which is 1 times J to the first power is just J, and it cycles and so on and so on. Going in the other direction, J to the 0, anything to the 0th power is 1. J to the -1, so that's 1 over J, which we could multiply by J times J, which gives us J over J squared is -J. J to the -2 is going to be one over root -1 times 1 over root -1 is 1 over -1 is -1. J to the -3 is J to the -2 times J to the -1. So that's -1 times -J is +J, and it cycles as well. Homework 23, problem 2. Let's take a look at it. Pardon? Oh, I'm sorry. You were asking if you could finish copying it. Go nuts. All right. Oh my goodness, I can't type to save my life today. All right, engineering 221. Homework 23. Problem 2, correct?
Yeah.
All righty, for this guy, find the Thevenin and Norton equivalent circuit connected to our impedance ZL. All right, so that's the wrong thing. I have too many windows open. All right, so hop back and forth so I can draw this guy. All right, so I have a resistor, capacitor. Here's where my impedance ZL is going to be disconnected because we're trying to find the Thevenin equivalent with respect to it. Voltage source, current source down. And let's see, 65, J180 minus J80. .30 angle negative 76. 0.5 angle 2. Make sure that's amps and not milliamps or something wonky there. All right. So we want to find the Thevenin equivalent circuit. So let's start out with something real easy and find the impedance first, right? Thevenin impedance. So to find the Thevenin impedance, this would be the same circuit, but with our sources turned off. All right, so I would argue that it's just 65 in parallel with J100. Anybody got any problem with that assessment? All right. Six, 65 times 100I over 65 plus 100I. 54.499 with an angle of 33.024 degrees. Ohms. All right, so the impedance is knocked out of the way, so we can have the Thevenin and or the Norton equivalent circuit by solving for V Thevenin or I Norton now. So which of those two is going to be less of a pain in the butt? Therein lies the question. So I'm trying to think. Obviously, if I short this guy out and measure that current, that's gonna have to require mesh analysis. There's no other way around that. There's 3 window panes, no practical voltage sources that we could convert to practical current sources, and similarly, no practical current sources that we could do to a practical voltage source to simplify anything. If I want my Thevenin voltage, it looks like if I do nodal analysis, I'm going to have 2 unknowns. Right, I don't know the voltage here. Let's call this Vx, and I don't know the Thevenin voltage, which is what I'm trying to find.
So it looks like this is use of the computer, you know, cut it. So which would you guys prefer, nodal analysis or mesh analysis?
Mesh, all right. Andrew, you said mesh, right? I'm going to pick on you and make you write our mesh equations. So let's call this guy mesh A, this guy mesh B, and this guy mesh C. So first things first, there is a current source. So what is my current relationship equation going to be? Equal to what? Yes. Alrighty, now let's do the super mesh around that current source. Negative, because we see the negative polarity terminal first, but yes. All right. C minus A equals 0. All right, and now around mesh A. All right, and obviously I Norton will be the exact same thing as IC. All right, so now we got to go find MathCAD. I need my keyboard for this one. All right, using a solve block, if I can find my mouse cursor, which I can't seem to do, so let's tap on stuff. So I have 3 keyboard. Work. Dummy. Experiencing technical difficulties. All right, started typing. Oh, and now my cursor popped up. Great. All right, so we have our mesh current IA. I'm going to give that a guess value of 1 angle 0 degrees amps. B, I will guess 1 angle 0 degrees amps. And IC, I will guess 1 angle 0 degrees amps. Then we had the equation IB minus IC was 0.5 angle 2 degrees amperes. Then we had negative 30 angle negative 76 degrees volts plus, let me just look instead of trying to remember everything. Negative J80 IB minus IA. Plus positive J. Oh, that's going to freak that thing out. I need to do it not that way. There we go. 180 J. Oops. Nope, capital W computer times IB, no, IC minus IA, is that right? Is equal to 0. And then we had 65 ohms times IA plus 180 J ohms times IA minus IC plus negative 80 J ohms multiplied by IA minus I. No. Slipped. B equals 0. Those three equations correct? All right. So if they are correct, then I will drop stuff into a matrix. IA, IB, IC, A, IB, and IC. We probably want our answer in polar form. Or I want my answer in polar form, let's put it that way. And just for the sake of argument, let's put it in milliamps. All right. While I am at it, all right, let me pop back over to WebWork to see what we're looking for here. So we want the Thevenin voltage, the Norton current, and the Thevenin impedance. So the Thevenin impedance, we calculated that a minute ago. So let's circle back around to that guy real quick. Where was it? All right, so that's what we had, but it wants it in rectangular. So I'm going to convert that really quick. $45.694 plus J 29.701. And maybe this time I will type something in to WebWork. This would be an example of something more in depth than I can ask you to do on the exam. So doing a Thevenin and Norton equivalent circuit problem using complex numbers is absolutely fair game, but giving you a problem that would require the use of a computer to solve for the quantities
is not fair. So it's both an example of something that is okay and isn't okay. It's the level of complexity of this particular problem, not the content, that would prevent me from putting it on the test. All right, so let's see if this works without me looking like a jackass this time. 0.694, 29.701. So let's check this. I'll be danged, we got it right. All right, now our Norton current, which is I3. So I'm going to put that in here real quick, actually. C7 we found to be, I'll be lazy, 65 ohms times 100 J ohms divided by 65 minus, no plus. All right. 552.295, where is web work? It wants it in amps, so that's 0.552 negative 66.489. Good dang. Cooking with gas today. All right, so now that I know what those two quantities are, what would I do to get V7?
I times Z.
Yeah, I times Z. So I'm just simply going to multiply those two guys together, which I'm going to do on my computer because I like it. All right, so V Thevenin would be IC times Z Thevenin. And I want that expressed as a polar form complex number. So 30.099 with an angle of negative 33.465. Great. So parts A, B, and C are taken care of. Now, it says the power absorbed by the load impedance if ZL is exactly equal to ZTH. And for part E, the power absorbed by the load impedance if ZL is equal to ZTH conjugate. So one thing that I want to point out here, and this is where a lot of you might get frustrated, is that it's asking specifically for the complex power. It doesn't say that, but it gives you S down here, which is for the complex power. So on your exam, I'm not going to be a jackass like that. I'm going to tell you exactly what quantity I'm looking for, not have any room for argument or anything like that. Another thing that could potentially trip you guys up when trying to work this problem with your numbers or whatever is the fact that the quantity Vs and the quantity Is are not expressed as RMS values, right? But our complex power relationships are based entirely on RMS values. So let's circle back around to this guy. So this should scroll up hard. So we have the following RMS phasor domain circuit. Okay, so we have, it should be an impedance. So this is ZTH, and then we are asked to work things when we have it connected to another ZTH.
this guy. So let me pop back over to WebWork real quick. All right, so CTH is 45.694. Oh, that was written literally right there, plus J 29.701 ohms. That same thing is going to go here, 45.694 plus J 29.701 ohms. What is the RMS value of our voltage going to be? What divided by square root of 2? So we're not going to divide this voltage Vs by the square root of 2. We're going to divide the Thevenin voltage by the square root of 2 because we've simplified this big ugly thing down. So this circuit right here with the resistor, the capacitor, the inductor, voltage source, current source, and a load impedance, we have simplified to this simple circuit. That's the whole point of Thevenin and Norton equivalent circuits, is that we can make that big ugly thing look like something very, very manageable. Thevenin equivalent circuit is just a practical voltage source connected to our load impedance. Norton equivalent circuit is just a practical current source connected to our load impedance, and it's going to make our power analysis on our load very, very trivial to do. So we need to make sure to divide our Thevenin our Thevenin voltage by the square root of 2 to get into the RMS phasor domain where we can apply our complex power relationships. So our Thevenin voltage was 30.099. So I'm just going to take that and divide it by the square root of 2. 30.099 divided by root 2 gives me a voltage of 21.283, and it's going to have the exact same phase angle, negative 33.465. And now we have units of volts RMS. All right, so we want to know the complex power absorbed by ZL when ZL is equal to 45.694. So we can determine that by figuring out what the RMS voltage over the load is and or figuring out what the RMS current flowing through the load is. So which one do you want to do? Which of those two quantities do you want to solve for? Or if it's both, how do you suggest we go about solving for either of those quantities? Okay, let's do VL. How are we going to do it? Sure. So the voltage drop, so our Thevenin voltage source sees two identical impedances in series. So what's your name? Braden? Race. Okay. Race has suggested that we simply divide the voltage by 2, which is effectively just applying voltage division, and he's absolutely correct. So VL is going to be VTH divided by 2 is 10.6416, so let's call it 642, with an angle of negative 33.465 degrees volts RMS. So I would posit that we actually now have enough information to solve for the complex power absorbed by this guy. You may recall on the day we talked about complex power that we found complex power. So SL, sorry, that should be a bar because it's not an RMS quantity, it's power, is VL multiplied by IL conjugate, which is the same as the magnitude, sorry, of VL squared divided by the conjugate of our load impedance. So we know the magnitude and we know our load impedance. So that would be 10.642 volts RMS quantity squared divided by 45.694 minus J 29.701 ohms. So let's see, so we square that and divide it by 45.694 minus 29.701 I, and we get 2.078 with an angle of 33.024 degrees volt amperes, or 1.742 plus J 1.132 amperes. All right, so keyboard back. 1.742. That is not a period, that was a comma. This is in Europe. Let's see. You're correct. So that one single piece of information, that voltage is the only thing extra we needed to figure out what the power is if we replace ZTH with ZTH. ZL with ZTH. Now let's look at the last part of the problem here. So it's the exact same thing, but instead of having ZTH, we have ZTH conjugate. So let me redraw our circuit with the equivalent, Thevenin equivalent being used. So that's 21.283 with an angle of negative 33.465 degrees. Here's ZTH. Here's ZTH conjugate. All right, so ZTH is 45.694 plus J 29.701 ohms. So here we will have 45.694 minus J 29.701 ohms. And crap. Here's our quantity IL. Sorry, that should be an RMS phasor. Here's our quantity VL. Which of these two should we, which of these two would you like to calculate? And there isn't a wrong answer, but there's a more right answer, I guess, is one way to put it. And so what I mean by that, I'll kind of walk you through this. So we have ZTH in series with ZTH conjugate, right? So by definition, the imaginary parts cancel each other out. So we could find our current IL is simply going to be VTH divided by twice the real part of ZTH. Or, right? Anybody got any problem with that? So that would be 21.283 with an angle of negative 33.465. That guy divided by 2 times 45.694 gives me 0.233 with an angle of negative 33.465 degrees amps RMS. Now our complex power will be the magnitude of our current squared times the impedance of our load, which is ETH conjugate. So that's 0.233 amps quantity squared times 45.694 minus 29.701 I. I get 2.481 minus J 1.612. So 2.481. So it's got to be rounding error here then. I couldn't have gotten the imaginary part right and not this. There we go. Yep. So once we got the Thevenin equivalent circuit, the analysis got ludicrously easy really fast. That is the beauty of Thevenin equivalence. We could have also used the Norton equivalent and done roughly the same thing. All right, so we have 10 minutes left of class and 23% remaining on the life of my laptop's battery. Brooke. Fall 2019, number 35. All right, fall 2019.
Yeah, while we're talking about that question, can you just like remind me real quick of the basics, like regarding questions like those, like reactive power and direct.
All right, so we're told that a composite load draws 5 kilovolt amperes at a power factor of 0.82 lagging. So kilovolt amperes is representative of what quantity? Is it reactive power, average power, or apparent power? Did I just think that question in my head, or did I ask it? We have units right here. They mean something. They tell us what type of power we're dealing with. So again, is it average power, apparent power, or reactive power? It's apparent power. Exactly right. Reactive power is measured in VARs, apparent power is measured in volt amperes, and average power is measured in good old watts. So that means that from this, we have enough information to calculate S old. It's going to be 5 with an angle of inverse cosine 0.82. Inverse cosine 0.82. 5 angle 34.915 degrees kVA, or in rectangular form 4.1 plus J 2.862 kVA. The load is applied by a 600 volt RMS source operating at a frequency of 60 hertz. We'll use that in a minute. The value of the capacitor needed to increase the power factor of the load to 0.975 lagging is what? So we need to figure out what the complex power is after power factor correction. which is going to be 4.1 divided by 0.975. So we're taking our average power, 4.1 kilowatts, dividing it by our new power factor. That's going to tell us what our new apparent power is, with an angle of inverse cosine 0.975. Tell me again why I have a positive sign in front of the inverse cosine function and not a negative. Has nothing to do with whether the angle is in radians. In fact, the inverse cosine is acting on a ratio. It's going to give me an angle, but that bit right there is not an angle whatsoever. So I think I had somebody say it. It's lagging, yes. So when the power factor is lagging, the angle should be positive. When the power factor is leading, the angle should be negative. All right, so 4.1 divided, hold on, let me go back through here. So where this is X. All right, so 4.1 kilowatts divided by 0.975, my power factor with an angle of inverse cosine 0.975 gives me 4.205, angle 12.838, or 4.1, so the average power stayed the same, which is exactly what it was supposed to do. J 934 kVA. So my next step, so I've calculated the old complex power absorbed by my load, which is the same as the complex power supplied by my source. I've calculated the new complex power supplied by my source. How do I figure out the complex power supplied by my capacitor? I don't add them. That's what I'm trying to find. How do I do it?
Oh, SU minus S whole.
There we go. So I take the difference, S new minus S old. So that's Y minus X in my calculator. Except I keep hitting the button too many times. Minus J 1.927. I don't understand your question. They do. So if we had an inductor, you would not put inductor in to do power factor correction unless you had a capacitive load, and those in practice pretty much don't exist. So in an industrial setting, you are going to have inductive loads because you're using inductive motors in your HVAC units and any heating unit, or well, I guess that would be covered by HVAC units. But if you have any conveyor belts or anything like that in your industrial application, any turbines, all that kind of stuff, those are inductive loads. To have a capacitive load, the only capacitive load that I can literally think of right now would be on a naval warship that uses a railgun. That's it. Whereas every other instance I can think of would be inductive loads, messing with your power. All right, so now that we know Q cap is just this value divided by J, C is negative 1.927 times 10 to the 3 volt amperes. Negative, these two negative signs are going to cancel each other out. What's omega? Based on the information you're provided in the problem. So you have a linear frequency of 60 hertz. So times 2 pi would be 120 pi hertz or 120 pi radians per second multiplied by the RMS voltage across our capacitor, which is 600 volts RMS, quantity squared. So let's see, we're going to have 1.927 divided by 120 pi times 600 squared is 1.4 times 10 to the minus 1.420 times 10 to the minus 5 farads is 14.202 microfarads.
Is that relationship with the capacitor in the formula? So, will be on the test.
This, is that on the sheet? Yes and no. And so let me explain that. Let me find that email again real quick. And open this up because I think I closed it. So way down here at the bottom, all right, there it is. So QC is omega divided by, or QC divided by omega volts RMS squared, or it's the average power multiplied by the difference of the tangents of the angle. I literally never use that one. I think I might have used it on the video thing, but this first one is the one I'm much more familiar with. So so QC is always going to be a negative quantity. Dr. Cronk just left it off of here for whatever reason.
What you, does it say anywhere on there what you see is?
Don't look like it, not my problem. I do not agree with, I'm going to allow you to use this stupid equation sheet, but I do not agree with you getting to use it. So, yes.
So like our, as well as one, or as well, like got rid of the, like, is that always gonna happen?
Yeah, it's always going to get rid of the real part. You're only, and that's the whole point of power factor correction, right? So your power factor, or excuse me, your angle S old is something like this. Let's call this guy theta old. When you do power factor correction, the point is to keep, I guess I made that too long. The point is to keep P the same while lowering Q. So if P is the same for S old and S new, when you take the difference, it goes away every time, yeah. So all that's going to be left will be the amount of complex power that the capacitor needs to be bringing to the situation in order to drop that power factor. All right, we are 1 minute over, so go away. If any of you have a lab that you need to make up, I'm going to be hanging out around here for the next hour or so to get those knocked out, if you want to do that.
Is there any other public problems we have? Didn't know about the, I'd ask about those.
You can ask them about them via email, and I will get to it when I get to it. I've got to upload all of the videos. I have to make the test. I have to upload the solutions to exam 1. So
Would the best way to email you about a homework problem be like to take a screenshot of the homework problem?
yeah, show me some work, because the first thing I'm going to do if you just send me a thing through WebWork that says I don't know how to do X, Y, or Z problem is, okay, well, what have you tried? So if you don't show me some work, I'm just going to tell you to start working the problem and then tell me where you get hung up. Let's see what's in the chat.